All right. Whoa. All right. Welcome back from the final coffee break, which is kind of scary. We're at the end stretch now. So there's one more What's New session that Paolo and I are going to do. Then there's another talk from Ed, and there's Roger's talk, which for those of you who've not been here before, you'll understand afterwards. And then we'll have a wrap-up session, and that's it. We're at the end until the hackathon tomorrow. So let's go ahead and get started with Paolo. Just put that in your pocket and then probably on the right and the left-hand side, because you're going to turn your head this way.
Okay. Can you all hear me? Yes. It's like, I will make this a bit larger. If we can.
So yeah, my computer, I fuck around with the keyboard, so.
Okay. Nope.
There you go.
Okay, thank you. So this is just some enhancement to the RDKit JavaScript library. So the one that allows you to use RDKit directly in the browser in web applications. Here I'm displaying this into Jupyter, which is itself a web application. So just a quick refresher, I have already presented this before, but not all of you may be aware of this. So in a Jupyter notebook, if you just, don't worry about this part, this is just about loading some settings that I like more than the standard ones. Greg is not agreeing with me, but that doesn't matter. And also setting these things is just to load the latest version because the standard one will not have the functionality that I need to display what I'm going to show. The real important bit is this interactive render set enabled. And by doing this, whenever you display a 2D structure of a molecule, it is not just a static PNG or SVG image, but it is actually an HTML5 object, which can be either a canvas or an SVG, but you can actually interact with it in different ways. So what I want to show today is just an application of this. So the idea is, how can you efficiently show atom-based properties on a molecule? Of course, if it's just a number, you could display an atom label, an atom node close to the atom, but you might have many of those, and you could have multiple properties that you want to show, and not all of those you could visualize with just some sort of highlighting or coloring, or just with a single number. You might have more information that you want to push. It could be a small table of numbers. It could be even an image. All of this will be possible with these atom-based visualizations. So this is just preparing a table with some experimental pKas. I'm not going to go through that. I just included it for completeness. I'm just getting the pre-computed data frame and just adding a molecular representation to it. And this is the familiar bit. So we just enable the rich visualization of molecule in the database so that they show up as images. But in addition to being images, since we have enabled the interactive representations, we also have copy-paste. So you can actually copy the molecule both as an image. So if you paste into PowerPoint, it will paste as an image. You can copy it as a mol block. So you can actually paste it in ChemDraw or in Marvin.js or whichever sketching software you prefer, and it will preserve the geometry. Or you can explicitly decide to copy. At some point. I promise it did. Oh, yes, it did. So, and you can explicitly copy SMICE or MolBlock or INCHI or PNG, and you can even increase the resolution of the image if you want to paste in a poster, for example. But that was already there. So what I'm going to show today is I would like to associate these pK values that I have in the table to the atom that they belong to. I don't have this information in the table. So first I need to be able to associate the pKa value, be it as acidic or basic, to a specific atomic center. And for doing this, I'm using MOCA, which allows to basically predict the pKa values, and I'm going to assign the closest prediction to the experimental value, and it will also tell me where it thinks that the acidic or basic center is in the molecule. And the sort of output that I get from there is this. So it's just a table where it says the number of acidic or basic centers that you have, the type, the predicted pKa, the index of the atom, and the standard deviation. And then this is just a few classes, and what these classes do is just they parse these results, they assign the experimental pKa to the closest predicted, and they set up the tooltips. And the tooltips are just defined as HTML text. So it can really be anything that can be rendered with HTML, including images. So what I do here is just parsing these predictions, assigning the closest, and preparing the molecule for this visualization. I just drop a few columns that we don't need anymore because we don't need the raw data because it will be actually displayed on the molecule itself. I just make the images a bit larger and then display the data frame. So as I was mentioning, yes, you can display the fact that the center is acidic or basic by the coloring of the halo. You can show either the predicted or the experimental pKa as a label, but you cannot show both. So if you now hover on the atoms, you can actually show more information. And I believe this could be pretty useful because it's not, it could be really anything. This is just an example. It doesn't have to be pKa's, it can be anything. Another application of this interactivity that I added recently is the possibility of doing selections. So this is just basically a wrapper class, which wraps a standard RDKit or arrow molecule. But basically, it overrides the HTML representation, so it adds also the interactivity on top of the usual representation. So if you instantiate this class with a molecule, I'm just taking one of the molecules from the previous data frame and visualize it as I would do with a molecule. I still see the molecule as I would do with a normal molecule, but now I can also do selections. So the selections can be atomic, can be bonds, and can be combination of the two. And if you press Shift as usual, you can select multiple. And the nice thing is that you can also access those from Python. So you could use this just in a standalone web application, but you can also use it in something like Dash or Streamlit or even in Jupyter Notebook, and you can actually access the selection that you are doing by interactively. So it's constantly synced. So I hope you find this useful.
Are there any questions on it before we move on? Patrick.
Currently, I tested it on. Yes, so the question is the browser support. I tested it in Chrome and Edge. I also tested it on Safari. It also works on mobile devices. And in the past, I also had built an Internet Explorer 10 version of this. Internet Explorer 10 does not support WebAssembly, so it was compiled to ASM.js. It's a bit slower, but it still works. So I assume that also this should still work. But I'm not sure you want to go with E10 these days.
Great, thank you, Paolo. Okay, so I'm going to move on to the bit more what's new. I have a bunch of things here. We won't get through them all. Again, the notebook will be available on GitHub or later after the wrap up. If people want more what's new, I can hang out and we can do more what's new. That's your call. So I'm going to start with heteroisomers. These are not super new. They came at the beginning of last year. I think people are not necessarily aware of them. I think the support is fundamentally useful, and it's not something you find in many other toolkits. I think it's just worth explaining in case you're not aware of it. So how many of you are aware of the heteroisomer support in the RDKit? Oh, that's more than I thought. Okay. For those of you who are not, the basic idea of an heteroisomer is you have a rotationally hindered single bond, it gives rise to chirality in the molecule. So in this molecule here, there is this bond you can think of as being a chiral center because it has four different substituents arranged around it in a tetrahedral manner. And so this molecule cannot be superimposed on its mirror image. It has a chiral center. The chiral center is a bond. This particular molecule does happen to be rotationally hindered, and so you actually can separate these two things from each other unless you heat the molecule way up. The two stereoisomers will not interconvert, the two atropisomers will not interconvert. The RD kit is capable of representing this situation. So if you give it a molecule which has a wedge bond like this, it's capable of perceiving that, recognizing that this bond is intended to be an atropisomeric bond and marking it, and I'll show you what that does. What the RD kit is not capable of doing is telling you that this bond is actually rotationally hindered. Right? So that's up for you to decide, right? That requires provided it. Okay, that's a very important disclaimer. At the moment, these atropisomers are currently parsed from and written to mol or SDF files, CDXML, MRV, and CX files. And it is work in progress. We're going to keep adding functionality. It is documented in the RDKit book how this stuff works. If you have questions about the representation or how it works, it's in the RDKit book. But let's start with an example. Here's that molecule. Let me make it a little bit bigger. Here's the molecule with the atom numbers set up. I can do debug on the molecule, and it tells me that the bond between atoms 0 and 1, so this bond, the bonds between atoms 0 and 1 is counterclockwise, and the counterclockwise refers to these four atoms. I'm not going to get into the representation now because it takes a while to explain. It's in the book, there's examples, but the information is in debug so you can understand what's there. We do correct SIP assignment, so the implementation of the SIP assignment that the RDKit uses knows how to handle these atropisomeric situations. So if you do SIP assignment and show the SIP labels on the molecule, it correctly labels that bond as being M stereochemistry. So that's the correct isotope or absolute stereo label for that. The information is used in conformer generation. So by default, the conformer generation attempts to reproduce the stereochemistry that you give it. And so like chiral centers, if you embed a molecule which has an atropisomeric bond, all of the conformers you get back will have the atropisomeric bond in the correct conformation, which is what we're showing here. If you turn off the chirality enforcement, then it ignores that, right? So it's the same as if you turn off chirality enforcement with a molecule that has chiral centers, instead of getting only conformers where the chiral configuration is correct, you get a mix. Here you can also get a mix of the atropisomeric bonds. Again, I'm not going to do the representation. That is in the book. If you read a molecule and it has 3D conformers or a 3D conformer associated with it, it will perceive atropisomeric stereochemistry from the 3D. So by the arrangement of atoms about that bond. But there is a caveat to that. It only does it if the bond is wedged on input. So if I provide this molecule, this is just a 2D sketch of the molecule, but if I provide the molecule in 3D and I wedge one of the bonds around the atropisomeric bond, that's telling the RDKit that it should interpret the 3D of that bond. It should use the 3D to interpret the stereochemistry. Right? If you don't have that, it will not interpret the stereochemistry because otherwise you would assign atropisomeric stereo to almost every bond in the molecule, and that's ridiculous, right? You need to tell it where these bonds are, where the rotationally hindered sites are. And then the last bit is you can also do this without a conformer. So there's a convention, and this is described in the book. There's a convention that you can use in CX smiles so that you can provide a CX smiles without coordinates and just say a bond is wedged, and it will interpret that correctly according to the conventions that it uses. So before I move off of this, are there questions about how the atropisomeric stuff works? Aside from people who are aware of this, or of the people who are aware of it, are you actually using it for anything? Yeah, okay. Good. I would like to see more use of this. I know this is relevant to a lot of people. There's a lot of companies that are doing these things now. There's some interesting properties of atrop-isomeric molecules that I'm not going to get into because it's chemistry, not RDKit. Yeah, it's fascinating. The other thing actually, which is being shown here, which I should mention while we're here, you notice there are some labels here that are blue and instead of being black. So one of the things I changed in the last release is that bond indices are now drawn in the molecule in blue instead of black. It used to be that atom indices and bond indices were drawn in the same color, and I could never tell which one was which, and somehow I put up with that for years. Um, I realized a few months ago I don't need to put up with that. I can actually just change it. So now the bonds by default are blue and atoms are black. So now you can have them turned on at the same time. Okay. One other quick thing before I move on to something that's perhaps more interesting is there was a change a couple releases ago in the way valences are calculated for charged atoms, or allowed valences for charged atoms. This is based on some feedback that Roger gave a number of times. It took a while to sink through my skin, or for me to have time to do it, or maybe Roger just kicked me one time enough that I did it. It used to be fairly complicated to figure out what allowed valences on atoms was, and it's gotten a lot simpler. So for things like carbon, you know carbon has 4 allowed bonds. We know nitrogen has 3 allowed bonds, and we know oxygen has 0 allowed bonds. N plus is nitrogen minus an electron, which is the same as carbon. So N plus has 4 allowed bonds. Right? N minus is nitrogen plus 1 electron, which is oxygen. So N minus is allowed 2 bonds. So it's very simple for the main group elements. You add or remove an electron, you figure out which element that turns you into, and that's the number of allowed hydrogens or number of allowed valences you have. This was particularly embarrassing because this maps to something called the isolobal analogy. I did my PhD with the person who came up with the isolobal analogy, and Roger really used to beat me over the head with that. So it's okay now. Are there any questions on this? This is just intended so you understand what's going on when you get a unallowed valence error on a charged atom. This is how you interpret what's going on. Okay. Let me talk about shape-based alignment. So I'm going to completely change gears. So the team at PubChem had on the back end, they have this PubChem 3D thing where they generate conformers for molecules. And in PubChem 3D, you could find, you can look up molecules that are shaped similar to the molecule, the 3D molecule that you're querying with. And they had code in the back to do this. That code was just internal to PubChem. It was stuff that they had written and you developed over the course of years. It was very highly optimized to their workflow. It worked quite well for their workflow, but nobody else could use it. And we had a series of conversations over multiple years to convince them to actually make that code open source. Where that happened at the end of 24, they did a fair amount of work to take this library, which is optimized for their internal workflow, convert it into a library that's actually usable by other people, and then made it open source. I put a wrapper around it, and now you can do shape-based alignment in the RDKit using Gaussians on the atom, similar to what ROX does. Not the same as what ROX does, but similar to what ROX does. The API is maybe going to change over the course of the next few releases as we change things. And it's important to remember this was internal code that was very highly tested in one particular workflow. And now we're using it in different ways. So there are bugs, which we're finding and fixing as they turn up, like anything else, right? So don't expect it to be perfect. I just want to show how it works. So here I bring in a bunch of molecules. I take the first one out to use as a reference. I generate conformers for all of the rest of them using SRETKDG. I then, just to show what we're starting with, here's the first 2 molecules, or the reference molecule and the first molecule, and you can see they start off nowhere near each other in this data set. It's a random collection of molecules. They had no reason for them to be aligned. And then I can import this new library, RD shape align. I start by canonicalizing the conformers of each of these molecules. Canonicalized mole, if you don't know what this is, it takes the molecule, translates it to the center of mass frame, and aligns it with the principal axis, the principal, aligns it with the principal axis, aligns the principal axis with the Cartesian axes. This should not be necessary. We should be doing this internally within a code. We will eventually do that, but now we highly recommend doing this. And then you can just align the molecule by saying align mole, and you get back now two molecules which have been aligned to each other using shape alignment. Then that's basically what the code does, right? You give it two conformers and aligns them in order to maximize the shape, potentially including feature scores, the locations of pharmacophoric features to pick the best alignment. The rest of this is just showing how you define the shape score or how you define the features, and how you can work with that in order to choose a set of conformers to work with. I'm not going to do that here. The notebook will be on GitHub. I do want to show some speed stuff because the ArtyKit had, hopefully nobody actually knows about this, the ArtyKit had some Python-based shape alignment code that is really, really, really terrible. So I never talk about it. It is still there. You should never use it. This code is faster than that. So I think I have timing information in there. Yeah, so this did on 3,700 alignments, it took about 4.5 seconds running on my laptop. So it's not, for people who are used to rocks, this is not blindingly fast, but it is still pretty damn fast. I mean, it's a perfectly reasonable tool for doing alignment. It takes about a millisecond per alignment. Okay, before I move on, are there questions about that stuff? I'm really happy about this. I've been wanting to have shape code in the ArtyKit for a long time because I think it's a really useful approach for picking 3D related molecules without paying enormous amounts of attention to atom types. Next thing I'm going to talk about is just a couple of improvements to, let's do some miscellaneous stuff. The first one is a really simple one that I think is hugely useful. So Hussein at Schrodinger did this. So the smiles and smarts parsers, if you have a syntax error in your smiles, they now tell you where it is. Or it used to tell you where it is, but they now show you where it is. So if you give it a smiles that has a problem in it, this at doesn't resolve to anything, so it's wrong. It now tells you where the problem is, right? It's simple, but I think it really helps diagnose problems. And I show here, there's an example where you open a branch and it shows you that you've opened a branch, not closed it. Same thing for the smarts parser. So really silly, simple, but hopefully useful for tracking down problems, particularly if you're not super familiar with smiles and smarts. Has anybody noticed that? It's been out for a while. Well, sad. Okay. I think it's cool. Sorry? You don't make errors, or you turn the errors off. Or, as I've noticed from some folks who I won't name, the error messages scroll by and you just ignore them, right? They're just warnings. Who needs to pay attention to those? Okay, next one. This is also, it's been there for a while. How many of you know about molezip? So there have been a couple talks where people talk about combining things like combining synthons or combining pieces, fragments to make a single molecule. If you are doing that and you're doing something like constructing an RW mole and adding bonds, you really shouldn't do that. This is a much better way to do it because this takes care of all of the bookkeeping to maintain stereochemistry properly. And do a bunch of other stuff. So molezip is a really nice tool for taking a series of fragments. Here's a simple example. I have 3 fragments in one molecule. The first has the dummy atom with a reaction map 2, the second a dummy atom with a reaction map 1, and the third one has 2 dummy atoms with reaction maps 2 and 1. When you call molezip, you get back a molecule where it's attached the 2s to the 2s and the 1s to the 1s, and you have a final molecule. It will take care of making sure that the stereochemistry doesn't get screwed up when you do this. It fixes valence problems. This is a much safer way to do this than forming the bonds yourself. This is code Brian wrote a few years ago, and we've continued to evolve it. You can use it with R group decomposition, which lets you do all kinds of super cool stuff, or at least I think it's cool stuff. So here I have a core, and I have a molecule, specific molecule that has that core. I do R group decomposition, so I get the core and I get the two R groups. You may notice this looks like the kind of input to molzip. So I can then give these back to molzip and it puts it back together and I get my molecule back. That is not interesting by itself, but if I decompose a bunch of molecules, if I have a bunch of molecules that have the same scaffold and different R groups, I can do R group decomposition across all of those and get all of the R groups, and then just start combining the R groups together arbitrarily with the core and having molzip put that back together. So I can basically get all of the molecules covered by this set of R groups without really doing any work. It's just calling molzip repeatedly on the output of the R group decomposition. I think this is really great. It's a really, really useful thing to be able to do. Okay, at this point, I shouldn't refer to Rachel's poster because hopefully everybody went to Rachel's poster already. The DCLV, this is this double cubic lattice volume algorithm for doing efficient calculation of molecular volume and surface area. That came in the beginning of 2403 release, I think. And there will be a new version coming in hopefully a reasonably soon release that is faster, better, and includes some stuff like allowing you to do 3D polar surface area, which I think is really, really nice. I have like 2 more minutes, right? How many of you have started a confirmation generation run or something like that, realized it was going to take 15 minutes, and then realized you can't hit Control C and have the Python stop the job? So you have to hit Control Z and kill it. You don't have to do that anymore. So this is another one of those things that sounds really simple. It turned out to be really hard to do. But we basically have it working now. So there's some of the long running tasks in the RDKit. If you hit Control C while they're running, it will just stop. You don't have to kill the Python process. And in some cases, it'll even do something sensible when it stops. The confirmer generation just stops and you don't get any confirmers. This also works in the notebook on things that are not Windows. And unfortunately, I'm working on a Windows laptop, so I'm not going to demo that. I'm shocked. I thought it worked on Windows, but fortunately, I tested it yesterday. So I'm not going to make an ass out of myself by doing it now. If you're on Linux or the Mac and you hit the interrupt button in the notebook, it will also interrupt the currently running calculation. This is one of those, I almost feel embarrassed talking about it, but it really is nice. Many of the longer running stuff in the RDK will now do this, so you don't have to kill the Python process anymore. So many thanks to Dave, who did the work to figure out how to do this. And we'll keep adding it to more things. So if you find other long running jobs you can't interrupt, please let me know and we will try to figure out how to add this Control C stuff to it. With that, I'm going to wrap up.